Today's topic is hardwood versus softwood dissolving pulp and its importance in viscose filament yarn manufacturing. In this slide, the left side image shows a hardwood tree like eucalyptus, and the right side image shows a softwood tree like pine. This section provides a comprehensive introduction to the fundamental distinctions between hardwood and softwood dissolving pulp used within viscose manufacturing processes. Hardwood pulp is derived primarily from angiosperms, broad-leaved species such as eucalyptus and birch, while softwood pulp originates from gymnosperms, including pine and spruce. Understanding these differences is essential for optimizing fiber conversion efficiency, chemical reaction consistency, and yarn quality in viscose plants. Hardwood pulps are characterized by shorter fibers, higher porosity, and better chemical penetration, which make them highly reactive during steeping, aging, and xanthation steps. On the other hand, softwood pulps contain longer fibers with compact structures that impart superior mechanical strength, contributing to sturdier yarns and improved spinning stability. Their fiber and structural features directly influence DP levels, reactivity behavior, filtration characteristics, and spinning performance. By comparing their physical, chemical, and process-related attributes, this slide sets the foundation for understanding the operational trade-offs involved when selecting hardwood, softwood, or blended pulps for industrial viscose production. Hardwood pulp is sourced from broadleaf tree species such as eucalyptus and birch, which belong to angiosperms, plants that reproduce through flowers and develop enclosed seeds inside fruits. Softwood pulp comes from conifers like pine and spruce, belonging to gymnosperms that reproduce via cones bearing exposed seeds. These botanical distinctions influence wood anatomy, pulp chemistry, and subsequent processing behavior. In viscose manufacturing, hardwood pulp is widely used as the base pulp because of its high global availability and lower production cost. Its fiber characteristics promote efficient chemical processing and easier overall plant operation. In contrast, softwood pulp is typically employed as a blending pulp due to its higher cost and limited availability, but it contributes significantly to mechanical properties such as yarn strength and spinning stability. The complementary nature of these raw materials makes combined usage an industrial standard for balancing reactivity and mechanical strength. Hardwood fibers generally range from 0.8 to 1.5 millimeters and exhibit a more porous structure, which enhances their chemical accessibility and improves reactivity during viscose processing. The porous nature facilitates faster penetration of sodium hydroxide and carbon disulfide, leading to smoother and more uniform alkali cellulose formation. Softwood fibers, by comparison, range from 2.5 to 4.0 millimeters and possess a compact, vessel-less structure dominated by tracheids. This compactness results in lower porosity, but imparts high tensile properties to the resulting fibers. As a result, softwood significantly enhances yarn strength, reduces fuzz generation, and improves spinning performance. The morphological differences between hardwood and softwood fibers thus directly affect process efficiency, reactivity profiles, and final product attributes such as uniformity and mechanical integrity. Both hardwood and softwood dissolving pulps exhibit similar alpha cellulose content, typically ranging between 94% and 96%, indicating their quality as dissolving-grade pulps. However, key differences lie in hemicellulose composition. Hardwood pulp is rich in xylan, while softwood pulp contains higher levels of glucomannan. Hemicellulose content affects swelling behavior, alkaline absorption, and the overall reactivity of pulp during viscose preparation. Xylan-rich hardwood tends to swell more readily and allows easier chemical penetration, giving it superior reactivity during steeping and xanthation steps. In contrast, glucomannan-rich softwood pulp shows moderate swelling but contributes to higher DP values, influencing viscosity and mechanical performance. These compositional variations must be considered to optimize process parameters for dissolution, filtration, and spinning. Hardwood pulp typically exhibits high Fock reactivity, 65 to 75%, and higher NaOH absorption rates, 18 to 22%, resulting in faster and more complete alkali cellulose formation. These characteristics support efficient xanthation and dissolution, enabling smoother viscose preparation with fewer processing irregularities. Softwood pulp, with FOC reactivity ranging between 55% and 65% and slightly lower NaOH absorption, reacts more slowly and requires tighter control to avoid inconsistencies. Nonetheless, softwood contributes positively to viscosity buildup due to its higher dP. The differences in reactivity between hardwood and softwood necessitate careful optimization of steeping times, aging rates, and chemical dosages to achieve consistent quality. In industrial practice, blending both pulps allows plants to balance high reactivity with desirable mechanical properties. Hardwood pulp, characterized by lower degrees of polymerization, dP, tends to undergo aging more predictably and uniformly, making dP control easier during viscose preparation. This results in more consistent cellulose chain depolymerization, facilitating controlled viscosity adjustment. Softwood pulp exhibits higher dP values and therefore contributes to higher intrinsic viscosity in the viscose solution. However, its aging behavior is more sensitive, requiring careful monitoring to avoid excessive degradation or variation, which may destabilize spinning performance. Despite these challenges, the higher dP of softwood is advantageous in applications requiring stronger yarn. Proper blending of hardwood and softwood pulps allows manufacturers to fine-tune dP distribution to achieve optimal spinning behavior, filtration properties, and final yarn quality. Swelling behavior plays a critical role in steeping and alkali cellulose formation. Hardwood pulp demonstrates superior swelling due to its porous fiber structure and hemicellulose composition. This results in uniform alkali distribution and enhances accessibility during subsequent xanthation reactions. Softwood pulp exhibits moderate swelling, mainly due to its dense structure, which restricts chemical penetration. While this reduces reactivity, it helps maintain stronger fiber integrity. In practice, hardwood's superior swelling facilitates smoother viscose preparation, whereas softwood must be carefully proportioned to maintain mechanical properties without compromising process stability. Understanding these swelling characteristics enables better control over reaction kinetics and product uniformity. Hardwood pulp generally contains higher fines content, which increases filter load and raises the risk of filter choking during viscose filtration. This can lead to pressure buildup, reduced throughput, and the need for frequent filter changes. Conversely, softwood pulp, with its lower fines content and longer fibers, offers superior filtration behavior, resulting in fewer clogs and smoother filtration cycles. This property is especially important for maintaining steady plant operation and avoiding downtime. Although hardwood is easier to process chemically, its filtration limitations often require balancing with softwood pulp in industrial applications. By optimizing the hardwood-softwood ratio, manufacturers ensure efficient filtration, consistent viscose clarity, and stable spinning performance. The spinning stage of viscose processing is highly sensitive to pulp characteristics. Hardwood pulp offers good spin stability but tends to generate slightly more fuzz due to its shorter fibers. Softwood pulp, with its longer fibers and cohesive structure, delivers excellent spinning performance marked by smoother running conditions, lower breakage rates, and cleaner yarn production. Softwood also enhances yarn uniformity and contributes to higher tensile strength. This makes softwood particularly valuable for applications demanding high-strength viscose fibers. By blending hardwood and softwood appropriately, viscose producers achieve a balance between processability and yarn performance, ensuring operational efficiency and superior fiber quality. Yarn characteristics are heavily influenced by the fiber length and structural attributes of the pulp. Hardwood pulp yields fibers of moderate strength and is suitable for general viscose applications, while softwood pulp contributes significantly higher tenacity due to its longer, more robust fibers. Softwood also improves yarn uniformity and reduces fuzz formation during spinning, leading to smoother fabric appearance and better overall textile performance. These mechanical advantages make softwood essential for producing high-strength viscose fibers, despite its higher cost. A controlled blend of hardwood and softwood is often employed in industrial practice to meet specific performance requirements while maintaining cost efficiency. Hardwood pulp is widely available due to large global plantations and faster growth cycles of hardwood species. This results in lower production costs and consistent supply, making hardwood the primary raw material in dissolving pulp markets. Softwood pulp, originating from slower-growing conifers and limited forest regions, is costlier and less readily available. Despite its higher price, softwood remains indispensable due to its ability to enhance yarn strength and spinning performance. Industrial viscose plants must therefore balance performance targets with cost constraints, often using hardwood as the main pulp and adding softwood strategically to achieve desired fiber properties. Modern viscose manufacturing relies on combining hardwood and softwood pulps to exploit their respective strengths. Hardwood provides process ease, high reactivity, and cost advantages, ensuring efficient chemical conversion and stable viscose formation. Softwood, although costlier, is blended to impart higher yarn strength, improved spinning stability, and cleaner filtration behavior. The ideal blend ratio varies based on plant design, product requirements, and operational conditions, but the objective remains the same: to achieve optimal reactivity, viscosity, mechanical performance, and cost efficiency. This balanced blending approach represents standard industrial practice for delivering high-quality viscose fibers. A well-structured pulp selection strategy is essential for stable viscose plant performance. Hardwood pulp offers excellent chemical reactivity, accessibility, swelling behavior, and cost benefits, making it ideal for base usage in viscose production. Softwood pulp complements hardwood by providing mechanical advantages such as higher yarn strength, improved spinning stability, and better filtration behavior. Together, the two pulps create a synergistic balance between processing ease and end product performance. Understanding how each pulp type affects dissolution, aging, filtration, spinning, and yarn characteristics is crucial for optimizing plant operations, ensuring consistent viscose quality, and meeting textile performance demands.